All right, so in this final segment here, I'm just going to give you another sort of phrasing of the condition for uniform convergence, and then we're going to look at a couple more examples and how we can use, um, how we can analyze them and understand why they do or don't converge uniformly. So so this is remark 24.4. So uniform convergence can equivalently be described as follows. So a sequence Fn of functions on S converges uniformly to a function f on S if and only if the limit as n approaches infinity of the supremum of f of x minus fn of x across all x and s is 0. And if you just think about this for a bit, right? If you think about this supremum basically quantifies the farthest distance, right? And this could actually be infinity because, maybe f is like, maybe s is all of r, and then f of x is some unbounded function, and maybe fn is like actually a bounded function or something. So this supremum could actually be infinity, but the whole point, the idea is that the limit has to be 0. And so the supremum sort of measures like the greatest distance between f of x and fn of x, or if you want to think about it like the greatest error in the approximation. If you think of fn as like an approximation, this is like the worst error basically that fn has. And so the idea is that like if the greatest distance between fn and f across all x and s goes to 0, then you can make n be really big, and the supremum will be small, basically, right? And if the supremum is small, that means the error across all x values has to be small, right? So that's the idea here. I'm not going to prove it. It's left as an exercise in the book. I'm not sure. I don't think I assigned it, but I don't know. I think it would be worthwhile for you guys to try to think about proving this on your own. So knowing this, this gives us kind of we can look at a couple examples. And well, actually, first, before we do that, I want to make a comment that this looks similar, right? This supremum here, this resembles the metric we saw on C of S, if you remember from just a lecture or two lectures ago, I guess, right? Or was it? Or no, it was, oh, whatever, it doesn't matter. Anyway, I showed you guys, so C of S is like a metric space. It's the space of functions, of like bounded functions on S, bounded continuous functions on S. And the metric is taking the supremum of the distance between two functions, basically, across all x values in S. Of course, in that case, all the functions were bounded and continuous, which kind of limited the scope of the definition. Because so in that case, it's like, well, what we can say is like, so if Fn converges to F as a sequence in the metric space C of S, then Fn converges to F uniformly on S. Okay, you can say that much. But the thing that's slightly different is that since C of S only includes bounded continuous functions, that's like what this definition would be limited to, basically. Like if you just defined, like Fn converges to F uniformly if it converges as a sequence in C of S, that would be too limited because that would only talk about functions that were bounded and continuous, when in fact the definition of uniform convergence in general actually applies to any functions whatsoever. Actually, I mean, they don't have to be bounded or continuous. Actually, this brings up what I wanted to make the lecture question. So this would be lecture 17, question 1. Give an example of a sequence Fn converging uniformly to a function f on R such that f is unbounded. Oops. Okay, so this is, well, yeah, we'll see. But remember to include this with your homework, and yeah, try to do it yourself and write your solution in your own words. Okay, so I'll go ahead and go through the answer here. I mean, so this is actually like way easier than, it's almost like stupidly easy. I mean, the easiest choice would be something like f of x equals x for all x, and then also fn of x equals x for all x. This is a very trivial example, very trivial. Slightly less trivial, but only very slightly. Take f of x equals x and fn of x equals x minus 1 over n, right? So then clearly f of x minus fn of x, oops, absolute value just equals 1 over n for all x, right? So, clearly by making 1 over n less than epsilon, we make fn of x minus f of x less than epsilon, right? For all x. Or alternatively, using the statement I just made, right? The supremum of this across all x in R would just be 1 over n, because it's literally just constant, right? It's just every one of these is 1 over n. So the supremum is 1 over n, and then clearly that approaches 0 as n approaches infinity, right? So there you go. So these are some very trivial examples, but the point is that our definition of uniform convergence, it applies to all sorts of sequences of functions, not just bounded continuous functions like in C of S. But for those sequences of bounded continuous functions in C of S which actually converge, those sequences also converge uniformly according to our general definition of uniform convergence. Okay, let's just look at a couple more examples. So all right. So uniformly convergent sequence. Say fn of x is x over 1 plus nx squared. Okay, so point-wise, clearly the limit as n approaches infinity of fn of x equals 0, right? Because if you imagine x being a constant and then n just approaching infinity. Oh, also, let's say, oh yeah, for x in R. Okay, so let's just say, yeah. Well, yeah, so for x constant, right, clearly as n approaches infinity, this just approaches 0, right? So the pointwise limit is 0, and then we also claim Fn goes to 0 uniformly on R. Of course, it's not that hard to show because there are some easy bounds you can get on the absolute value of Fn of x just for all values of x. But what we can do is, using our new characterization here, we can say that if we can just show that like the maximum and minimum values of f of x, of Fn of x approach 0 as n approaches 0, that's enough to show, right? So according to remark 24.4, it suffices to show that the maximum value of f of x, of Fn of x, sorry, I guess maybe I should write it like this, Fn of x for x in R goes to 0 as n approaches infinity, and the minimum also. Right, because if the max and the min go to 0, then the absolute value of Fn, the maximum absolute value, or the supremum at least, right, which actually does, well, in this case, for these functions, it does get achieved. But yeah, the supremum of the absolute value of Fn of x will go to 0 in that case too. So, okay. So then we can sort of cheat and use calculus. You know, solve Fn prime of x equals 0, yada, 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 yada. So we find, I'm not going to go through it all, that x is plus or minus 1 over square root of n, and f of plus or minus 1 over square root of n equals plus or minus 1 over 2 square root of n, where the signs are corresponding. So plus 1 over n, 1 over square root of n gives plus 1 over 2 square root of n, and vice versa. And like minus 1 over square root of n gives minus 1 over 2 square root of n. So clearly both max and min go to 0, right? So that shows that it converges uniformly. On the other hand, let's look at another sequence. So Fn of x equals n squared x to the n 1 minus x for x in 0, 1 closed interval. So then clearly Fn of 1 equals 0 for all n, and the limit of, right, the limit of Fn, well, okay, for x in 0, 1, open on this side, we have the limit of n squared x to the n equals 0 as n approaches infinity. This is hopefully becoming familiar now that these exponential functions, they'll decay faster than any polynomial function can grow. So one way of seeing this would be to take the nth root of this, and then you'll get something that approaches x, and then since x is less than 1, that means that you can basically compare this to an exponential sequence. Well, I don't know. They cite an exercise in the book, which I don't remember if I ever assigned. I think I did, actually. Yeah. So you can use that. I think it's 9.12. So exercise 9.12. Yeah. If you want sort of a really rigorous way of proving this. Anyway, so this goes to 0. So since fn of x is just 1 minus x times this, that also goes to 0, right? So fn goes to 0 pointwise on all of 0, 1. Okay? So, but let's show that actually the supremum of the absolute value of fn of x for x in 0, 1 actually goes to infinity. So the maximum of f of x, and since fn of x, but since fn is positive for all values of x in 0, 1, so we can actually just drop the values here and also just like make this be a maximum, because it actually does get achieved, especially since it's a closed interval here, then it has to get achieved, right? So the maximum of fn of x for x in 0, 1 so there's calculus that happens, turns out to be fn of n over n plus 1. Okay, if you just go through the algebra, I'm going to skip it for now, which is n squared. Well, okay, I'm just going to give the sort of the final expression for it. So n squared over n plus 1 times n over n plus 1 to the n. Okay? And this we've seen is actually, so this, I'm actually going to rewrite this. So this is n squared over n plus 1 times n plus 1 over n to the minus n, which is n squared over n plus 1 times 1 plus 1 over n to the minus n, right? Now this here converges to 1 over e, right, which is some constant. This, on the other hand, converges to infinity. So fn of n over n plus 1 converges to infinity. Okay? Or not converges to infinity, sorry, diverges to infinity. I don't know how many times I've made this mistake. Anyway, yeah, so the maximum value actually grows to infinity. If you want to see a picture of this, here, I'll draw a picture. So as you can see, so here's a picture, right? So as you can see, as n increases, basically like the peak gets squished more and more, like closer and closer to x equals 1. So if you picked a value of x like way closer, like super close to 1, for example, like let's just focus our attention on some value of x that's extremely close to 1, right? And then look at the value of f1 at that value of x. It's going to be pretty small. f2 is also going to be pretty small, but it's actually bigger than f1, right? f3 is small. It's bigger than f2. f4 is still kind of small, but it's still bigger than f3 at that value of x. But eventually, right, as n gets really, really big, the peak of fn will eventually move to the right of the value of x that we picked. Like if we picked some value of x that's strictly less than 1, eventually this peak is going to move all the way to the right, because look, the peak occurs at n over n plus 1, right? So as n approaches infinity, this gets closer and closer and closer to 1. This actually converges to 1, right? So the peaks get closer and closer to 1. So whatever x value we pick at the beginning, eventually as n gets big, the peak is going to move past that x value. And then once that happens, the value of fn is going to start decreasing at that x value. And then eventually it'll decrease all the way to 0. So you can see that happening like over here, for example, like at this, like say x value over here, right? Oops. Right, some x value over here. At f1, it's kind of small, right? At f2, it's bigger. At f3, it's even bigger. But then at f4, it's smaller again because the peak moved past, right? So and then eventually it'll just like decrease all the way to 0. So like also, let's say over here, for example, right? F1 is kind of big here. F2 is even bigger, but then F3 is smaller. F4 is even smaller. Sorry, and then all of the ones after that, they just get smaller and smaller and smaller, and this part just gets flatter and flatter and flatter. They all approach 0. So eventually, fn at any value of x, fn eventually approaches 0. It just might take a really long time. But as that's happening, the peak values, which get closer and closer to x equals 1, still end up getting bigger and bigger and bigger. So the convergence is not uniform. Even though the limit, in this case, the limit is also continuous, right? The pointwise limit is just 0 on the entire interval. So the pointwise limit is 0, but the convergence is not uniform at all. Okay. So anyway, so that's it for this lecture. That's uniform convergence. So yeah, I'll see you in the next one.